So let's do a roller coaster. I'm going to start off up here, and I don't know, we can call this height like H. And I know that the radius of this thing is, I don't know, let's call it like 10 meters. I want to know what is the minimum height this thing needs to be for me to just make it around. Let me repeat that. What is the minimum height this needs to be for me to just make it around? What do you think? So let's think about this. What do I have? I have here, let's see, my potential relative to whatever height this thing is. Then I have this radius here. At this radius, if I want to think of it from here to here, I look at that and I'm like, okay, that's a radius. This height then is 2 times r, otherwise known as, oh, we'll just run with that, 2 times r. 21. So let's think about what's happening here, because the biggest temptation that people have is to say that there is no kinetic energy here. I'm going to say, okay, at this point in time, for it just to make it around, that means that it's all potential. I've taken all this potential and converted it to that potential. Now, first of all, wouldn't that mean that they have to be the same height? So if that's not the case, then it seems to me that we can't use just energy. So the question we're solving here is how high is H to just make it. So now we need to think about this picture in terms of something different. Well, I kind of feel like there's a question that y'all have been asking, and I've been letting you chew on it because that's really the best way to wrap your brain around it. Is what's happening here? Are we doing something in terms of circular motion and forces needed to make you go into a circle? And that's something we're working on right now. And if that's the case, I'm going to draw a new picture here. Yeah, let's do this. So here is my roller coaster car. So if I'm going in a circle, what forces are acting on me here? I have the force of gravity. I can see everybody's getting that. And the one that's messing with everybody's mind is you say, okay, the force normal always goes opposite the gravity, always. That's not what I say. What I say is the force normal is always perpendicular to the surface I'm on. In fact, let's ignore the gravity for a second. Now let me turn this picture up like this. The cart is resting on the track. What direction is that normal? Because most of you at this point in time would easily go, oh, yeah. So I have a normal that away from the track. And you'd be correct. When I go like this, the only thing that's changed, whoops, I should have written it upside down. Yes, there's the normal. The only thing that's changed is now both gravity and the normal are in the same direction. So our normal is always perpendicular to the track. I can go like this. I can go then force normal. So here's going to be my center seeking acceleration plus, I say that this weight is positive, plus the force of gravity equals mv squared over r. Cool. So I have this. I've done forces. Then I'm like, but how the heck, I don't know what v is. And what about this normal for just making it around? What does that mean? So when you see that term, to just make it around, that means my normal is 0. Split second, very fast, still 0. So that my only center seeking force is this force of gravity. So for this picture here, to just make it around, my sum for my center seeking forces, well, that is, let's see, force gravity equals mv squared over r. Cool. Now let's think about energy here. So we know that we have potential here, and we know we have potential here, mgh2. And we also know that we have kinetic, because we just talked about that. So what I have, if I write this out in terms of an equation then, is I'm starting off with potential, and that's going to my second potential. I have some height above this 0, plus 1/2 mv squared. And I'm feeling kind of good, because what I'm wanting to do is relate this radius to this height somehow. And I look at this, I'm like, but if I haven't been, what am I going to do? How can I get this thing in terms of r? So let's see. This thing here becomes mg equals mv squared over r. M's cancel. So v squared equals the square root of gravity times r. I'm sorry, v squared, oh, I skipped a step, equals gravity times r. Oh, well, that's this. I can rewrite this. So I have mgh. Actually, let's leave. No, we're good. We're good. mgh equals mgh2 plus 1/2 mgr. Oh, sweet. Look at this. Look at this. So what is the radius? The radius is this thing. Oh, look, I wrote that as 2r. So I can write h2 in terms of r, and I can cancel. Let's not write these masses over and over again. And see, and I look at that, and I'm like, oh, g is also in everything. So h equals h2. Well, h2 is just 2r, right? It's just the diameter, plus 1/2 times, oh, look at that. So I can rewrite that if you want to do this, so you can see where the fractions are going to come from. So the minimum height for this thing to just make it around is 5/2 r, otherwise known as 2.5 times the radius is how high this needs to be to let just energy get us around this where we don't fall off. Bada bing.